Thank you very much. And thank you very much for organizing this memorial session of the workshop. This is, I think, a great idea. I yeah, I was very saddened to hear about Frank's very early and untimely death, and I yeah, it was kind of was a shock. I didn't know what's what happened, and I still don't fully understand it. But we all miss him, and I think we all agree it was way too early. Um, and only a few months after his death, it was that um, I sat together with a colleague, Igor Pak from UCLA, and it's now we got to talking, and we got to talking about one of the problems, or the main problem actually, that's now the kind of the most prominent problem that I learned from Frank when I just arrived in Berlin to do my PhD. And I want to talk about the solution to that problem, um, and its relation to topology. And I want to talk a little bit also about a variant of that problem that is interesting to algebraic geometers. Um, I will just touch on that part a little bit. It's a topology conference, so I will not go too deeply into that. But there's a variant of this conjecture that is also interesting to topologists, to algebraic geometers. Um, so what is the problem? It's rather simple, and it's also very related to things that you will hear about later in this session, and it is also very much related to things that you will hear about in this week, depending on which of the talks you go to. The one of the kind of the nice and elementary factor that's kind of as old as PL topology itself is that a PL homeomorphism is really a combination of rather elementary moves, and then you can ask yourself, what are these elementary moves? So which ones do I allow? And one of these, okay, so you might know Pachner moves. These are these bistellar kind of these kind of flips and flops that you might remember from um, Pachner's main theorem. But there's also another move that is called the stellar move, and the stellar move, basically, if you have you start with your simplicial complex. And if in the plane, there are not many choices. So for two-dimensional, there are not many choices. So in the what you take your simplicial complex. Let me kind of make sure that it's clear that this is kind of these faces are there. And what you then do is you pick one of its elements, or one of the simplices, and then you want to basically remove it and replace it with something final. So what you could do is you could, for instance, pick um, this this simplex here, right? I'll color it, and you want to remove it, and you want to remove with it every face that contains it. So you kind of leave a hole. Let me just make another drawing of the same kind, and then so I remove it. Everything that contains it. And then I want to, okay, but now I changed the topology, of course. So, and I don't want that, right? I want a new combinatorial object that has the same topology. And so what I do is I look at what I removed, and I basically cone over the boundary, right? I left a hole here, right? This hole is kind of um, the boundary of this triangle. That's my hole, and I take the cone over the boundary to fill it again. So I take this like this. All right. So this would be one of the possible stellar moves. I mean, it's called stellar move. I don't know the history. I don't know what happened back then. It could be that they just looked up at the stars and said, I came up with this. But of course, somehow, if you think about it, it makes sense because you cone, right? And now it looks like a little, right, more a stellar figure here, right? This is one of the possible moves, right? But I could also remove any other face and perform this procedure. So I could have also said, well, I take this edge here, and this is the face I remove, right? And then I have this hole, and then I fill it in again to preserve the topology, like this, right? By coning over the boundary of the hole that I have left. Okay? And so these are the stellar moves. And of course, if you have a stellar move, this preserves the topology. It's not hard to see. And then you can also, of course, go with the inverse, right? Right? So you have a stellar move and the inverse. And one of the theorems that is kind of the birth of PL topology, and it is due to Alexander. But then I should say it's kind of rediscovered also by Newman. So it's around in this area when all this kind of all the topology all the kind of these two tools of topology that we talk about this week were born, is that if two spaces, two polyhedral hydra are PL homeomorphic, so they are connected by a homomorphism that is actually it's stronger than just a homomorphism. It's a piecewise linear map if and only if they are connected by stellar moves and inverses. Okay. So this is the theorem. There's someone in the waiting room. Should I just let them in? I don't know. Bartosz Nesrecki. So I will just let them in. I don't know who that is. Okay. I'm not. Apparently, I have like a host rights, so um, I just let them into the room. Okay. Now that's the theorem, and so let me just illustrate it. So I have two spaces, two polyhedra, so P and Q. So these are just some triangulated, or even not triangulated. I can do this with polyhedral, like locally polytopic spaces or cell complexes, whatever you like. And I know that they're PL homomorphic, right? So they're PL homomorphic, and this means that then there's a sequence of um, uh, subdivisions, right? I remove. I look. Let me look at some more. An up arrow for me is a subdivision, right? A stellar subdivision. I can and inverses. So I write an up arrow just more like to visualize, because I want to say this increases the number of faces, and inverses. So this sequence can look like this until I end up at Q. Okay. And that is somehow okay. So that's a very nice thing to do, right? I mean, now I basically construct one way of thinking about this. This is kind of I factorize this PL homomorphism into kind of very elementary moves. And one of the first questions that arose in this subject and that stayed open for well until a year ago was the following. So, question. Is there a way to reshuffle these moves such that the subdivisions come before the inverses? Or in other words, does there exist a common stellar subdivision of P and Q? And this was first asked by Alexander. So this was in his original paper in 1930. This was asked, and this was the question that Frank asked me. This is the kind of the first question that actually I remember him asking me. So it might be also the first question that he asked me, but it's also one of the first questions in PL topology. So just to illustrate, this means that I have P, and then I do all the subdivisions first. I arrive at some intermediate space I, some intermediate simplicial complex. Then I do my inverses until I end up at Q. All right. So in other words, I can say I have this polyhedron I, and I obtain it by stellar subdivisions from P and from Q. All right. So I only at some point I decide, okay, now I just go down again, and that's it. All right. And this is a question. Right. It's and you can already see if you look at simple examples that perhaps this is not so trivial, right? So for instance, if I have this space here, right? Then I could look at the following subdivisions. I could perform a stellar subdivision in an edge on the left, like this, right? And I could perform a stellar subdivision in an edge on the right. And now I can ask myself, well, okay, so what is now I have these two spaces that I know are triangulating the same topological space, right? They are clearly parallel homomorphic. They're still, I mean, they're still triangulations of a two-dimensional disk. But how do I find the common stellar subdivision, right? So if I just naively overlay them on top of each other, right? So I could just, right? If I just naively overlay them on top of each other, then I end up with something that is not a triangulation. So I could just all right, I have this here, I have this here, I have the diagonal, and I have the diagonal, and you see that this is not even a simplicial complex. All right, this is not a This is not a stellar subdivision, not stellar. And so you see that there's something there's something that goes wrong, and so it's not an obvious conjecture, which I mean it had been open since 1930, so I better hope that it's not obvious. But you see that there's something of an issue, and there's something that you need to be doing. And the theorem is that theorem of myself and Igor Park. And I don't know, I don't remember the archive number, but you can look it up. It's from last year. And this is the Alexander conjecture, or the Alexander. Let me say, I asked it as a question now. So Alexander's question as a positive answer. Okay. So in other words, yes, we can reshuffle the moves, or yes, in other words, any two triangulations, right? In particular, any two triangulations of the same space. So for instance, of the same space. So for instance, a PL disk of the same dimension have a common stellar subdivision. Okay. So let me, before I go on and try to explain to you the proof a little bit, let me describe why people were why suddenly algebraic geometers became interested in this, and I will just briefly mention it because I mentioned it in the title. There's a name Oda in it, right? So a quick interlude. Why do algebraic geometers care? Um, so the story goes as follows. So one thing that algebraic geometers, in particular birational geometers, are interested in are varieties that are connected by birational isomorphisms. So they have two varieties, X and Y, and these are connected by some birational isomorphism. It's a special kind of map, similar to the way you think about a PL homomorphism. And what they wanted to do is, okay, so they wanted to also connect these by some elementary moves. And it turns out that also there are, in this case, elementary moves. And what you can ask yourself is then, okay, so these elementary moves are called flips and flops. These are similar to what the stellar subdivisions and the inverses. And then you can ask yourself, well, is there say a way to reshuffle them? And if in the language of algebraic geometry, you can ask yourself, is there iterated blow up if you have these two spaces X and Y that are birational isomorphic, is there an iterated blow up Z that is small, a blow up of X and a blow up of Y, right? And so this is the question that algebraic geometers ask themselves. And if one restricts to toric varieties. So toric varieties. So one of the kind of innovations of this birational geometry is that often these things can be reduced to polyhedra, and the reduction to polyhedra is basically by saying, okay, I can reduce this to a case of toric varieties. And the case of toric varieties is again a case of simplistic complexes. And then Oda asked, so question, given two birational toric varieties, does there exist a common blowup? And now it's a kind of I will say it like this. So a common blowup, and now you can kind of restrict. You can ask yourself at rationally smooth centers, so rationally smooth, and it's smooth centers. And these are two variants of the question. And this is by Tadao-Oda. And this is much more recent. Okay, so this is a much more recent version of the much more recent question. In particular, Tadao-Oda is still alive. And okay, so I will not go much into the algebraic geometry world. Let me just say the following. So the following implications are true. So the smooth order implies the rationally smooth order implies the Alexander conjecture. And I will try to explain it a little bit what this means, but the theorem, so our theorem is that in fact the rationally smooth order is true. Is true. And what is open is the so-called smooth order conjecture. Let me just explain briefly what is happening here and what is going on. And let me just go back to the start when I defined the stellar subdivision. Okay, so what is happening here when I'm talking about rationally smooth and smooth order? So if I'm talking about rationally smooth, okay, so notice when I defined the stellar subdivision, so I removed an edge, right, this edge here, and then I coned over the boundary, right? And of course, I basically just wanted to preserve the topology. And there are choices, right? I could have put, so I removed this edge here. And I just want to fill in the hole again. I could have done it, I could have coned with this apex here, right? This is my new this is the cone point, this little stellar point that I use to fill in the hole again, right? The rationally smooth order says, okay, this is not okay. The order conjecture is basically just restricting where the point can be. The rationally smooth order basically says that no, this is not okay. Not a good, not a rationally smooth stellar subdivision. the rationally, so this is not good for him, but what Oda basically said is canonically this new point that I put here, it should be in the kind of in the geometric locus of the edge that of the simplex that I removed. So I'm only allowed to put it here, somewhere here. And in fact, he asked a little bit more. He basically asked that this point here is a rational convex combination of the two endpoints. All right. So I can put it anywhere here. I can also put it here. I can put it here, but it has to be in this kind of in geometrically where I remove the face. Okay. And let me also say what the so basically the order conjecture, the smooth order conjecture that is still open, and so you can still, you know, if you're hungry and want to solve an interesting and big conjecture, this part is still open. The smooth order conjecture basically just says there's no choice. There's no choice where I put my point. I'm only allowed to put it at the barycenter. Right? I remove this edge, and I'm only allowed to put this new point at the barycenter of the simplex that I removed. Okay, so it's kind of a unique geometric choice. So in other words, the order conjecture is combinatorially is kind of the same as the Alexander conjecture, but it restricts the geometry. Okay, that's all I'm going to say. And just to make clear again, the smooth order conjecture is still open. And I want to tell you a little bit about. I want to try to give you an intuition of the proof, and I will do so in the plane. Okay, so for the two-dimensional case, and then I will try to explain what is different in the higher dimensional case. Okay, so if you have questions about the statement of these conjectures, ask them now, because now I will try to explain it a little. Oh, yeah. I don't want to note here. I don't know what happened. Okay, ignore the yellow post-it. Yeah. Um, no, even okay. So I mean, there's a trivial case that you can ask for one-dimensional complexes. It's kind of, I mean, polygons. There it is known, but even for two-dimensional polyhedron, so um, for three-dimensional toric varieties, all right? So fans is more usually for toric varieties you talk about the fan structure, right? And so the you have you would talk about a simplicial fan that covers D, and the two-dimensional simplicial complexes would correspond to the three-dimensional fan, right? And this is kind of the first non-trivial case, and also the first case I cannot really draw on this notepad is, and already that case is open. Okay. So already the case of two-dimensional polyhedra is open for the smooth order conjecture. Okay. Thank you. Good. All right. So let me try to give you an intuition of what is going on. Um, and I will try to, okay, so I will basically argue to you that it's all about finding a nice decomposition of a polyhedron. So let's say I have what I will look at is the notion of a fin. So I will look at the notion of a fin, and I will first look at a so-called striped fin. Okay, so a notion of a striped fin. So what is a striped fin for me? Well, this is a star-shaped polyhedron. Okay, so um, let me define first fin. Definition of a fin. And this is a triangulation of a star-shaped polyhedron in RD with a center V in the boundary of fin T in the boundary of T. And such that V is in general position with respect to the boundary. So I will have to try to explain what I mean with this general position, but the notion is quite simple. So I have a triangulation of some star-shaped polyhedron, and I have a point V somewhere in the boundary that is the center with respect to this triangulation. Okay? So now what do I mean by general position? I will try to explain it quite briefly. So I will define the following. So there's a horizon, and the horizon of V of T with respect to V, this is the minimal subset of partial of the boundary of T, such that if I cone okay, definition of a fin, right? And we were looking at this star-shaped set with the center somewhere in the boundary. Let me try to recreate the drawing. And the horizon was the minimal subset of the boundary of T, such that if I take basically the cone over this horizon, I will write it like this, over the horizon then the underlying set of this is the same as the underlying set of T. And the general position condition is that this minimal subset is closed. So V in general position if and only if this subset HRV, this horizon V, is closed. It basically just means that, let me just illustrate this. It basically just means that I don't have an edge on the far away part, right? So the horizon is kind of the far away part of the boundary. And in general position just means that if I look at this far away part of this boundary, right? Or the part of the boundary of this simplicial complex that does not contain V, then none of these edges here, none of these faces here in the far away contain V in their fine hull. Okay, so some edge like this, it's right. So this here would be bad. This edge here would be bad. And you see, by kind of wiggling this point a little bit, I can make sure that this is the case. Okay. So this is a kind of nice general position condition, and this is just makes life a little simpler for me. It's not really something necessary, but somehow it makes life simpler going forward. So this is my definition of a fin. Now there's of course a kind of a special fin, and this is I can look at if given a fin T, I can look at the following triangulation. All right, I can look at the cone over this horizon. All right, and this will be another triangulation of the same fin. Right, so for instance, if I looked at this case here, all right, then okay, I would look at the horizon, right, this red part, and I would cone over it. So this kind of special triangulation, it would look like this, right? The boundary would look the same, almost the same. Right? But then the interior would be just basically coning over the boundary, like this. And I call this the stripe of the fin. Of the fin T, or the striping of the fin. Okay? So it's just a special triangulation. And what I do is further, I call a fin scaled if okay, so now it gets it's a little bit more complicated. If the radial projection from T and I remove V to the horizon is a simplicial map. That is, it sends simplices to simplices. Okay, so what do I mean by that? Usually it's the best thing to give a non-example, right? And the non-example here is the one I drew before. So, all right, I drew this example, and I have my my center V here, my anchor. And now what do I notice? Well, for instance, if I took, what do I mean by the radial projection? Well, okay, so if I have any point here, any point inside my fin, there is a line through V that also intersects the horizon. Maybe I should do it in this kind of cute rainbow color. And I send this point here to the horizon. Okay? Of course, this is not well defined for V itself, but for all other points, it's well defined. So this radial projection here sends me to the horizon. And I want it to be a simplicial map. And in this case, it is not a simplicial map. Yeah? Let me draw the example again, just to make it clear. Right? If I look, for instance, at the radial projection with this center of this edge, it sends this edge to these two red points. So in particular, it sends one simplex to two simplices. So it's not simplicial. All right. It also sends, right? And even if I delete this outer part here, all right, now you could ask, is this scaled? And it is still not. It's because it sends this vertex here to the interior of this simplex. So it's not a simplicial map. It doesn't send simplices to simplices. All right. This is a condition. So a scaled fin, it kind of looks like a scaled fin. So it looks like this, right? I have a triangulation, and now it can look in the interior like this. All right, this is the way that it's. All right. And now what I want to look at this Alexander conjecture just for scaled fins and stripes. Okay, so let's look at just for scales and stripes. And it turns out that this is the most important case. You can reduce it to this to essentially this case. If I have time at the end, I will try to explain it a little bit, but that's the essence. So let's just look at scales and stripes, and notice now that this is very similar to stars and stripes, but I'm not patriotic at all. I'm not even American. So, I want to look at this case of a scaled fin. So T is a scaled fin. And S is its stripe. And let me look at this case first in the plane. Okay, so let me look at this case in the plane. So I have my scaled fin. And I have the associated stripe. And the associated stripe looks kind of similar. Okay, and now what I claim is that Alexander conjecture is actually kind of simple for this case. Okay, claim T is a stellar subdivision of S. So how do I achieve this? Do you have an idea? Do you see how to do this? I claim that it is all about something that will come up in Bruno's talk again, all about decomposing the space in a nice way. All right, so let's try to find this kind of magic decomposition, and how does it help us? So I claim that there's a stellar subdivision. So I want to look at I want to say that a vertex W in the horizon is exposed if there exists a unique edge of T not in the horizon containing this vertex. So let me give a non-example, all right? So I have my scaled fin here, and this vertex would not be exposed, right? Because there are three edges in the of my fin that contain this vertex and that are not in the horizon. Actually, this and this and this. This vertex is also not exposed, all right? Because there's this edge and then there's this edge. All right, but this vertex here and this vertex here, those two are exposed. Okay, so now let's think of this as if we were doing a collapse. So we have this exposed edge, assuming that it exists. Assume W is exposed. What can I do? Well, okay, so I can look at this edge that contains me. All right, this edge here would be the unique edge that it contains me. And there's a unique vertex on the other side, right? There's a unique vertex on the other side, this vertex here. All right, it's kind of a complementary to the exposed vertex. All right, I look at this vertex and I perform a stellar subdivision here in the stripe. All right, perform this stellar subdivision, it looks like this. Notice now that this part here and this part here look the same. All right, so they're geometrically the same simplex. So what I do is I just forget about them. I fix the triangulation at this point. I just forget about them. All right. I already made the triangulation look the same in this part. I'm done. And now what I do is I look for the next exposed vertex, right? I could, if there's another exposed vertex, so in this case, this vertex would be exposed, all right? I look at the unique complementary vertex here. I mark it on this edge here, and I perform a stellar subdivision. And it looks like this. And notice now this part looks the same, so I kind of forget about it. Right? I already fixed the triangulation in this part. So what I'm left with is only this polyhedron here. Right? Only this smaller fin here. Right? It contains it's really smaller because it contains less interior vertices. And I look for the next exposed vertex. So the next exposed vertex, if it exists, helps me continue the process. So what is exposed now? Well, in this new complex, right? I think of it. I removed this part. I removed this part. So what is the next exposed vertex? Well, this vertex here is exposed because this is the only edge that contains it. So I mark it and I perform a stellar subdivision and done. Right? Now the complexes coincide. We're done. So we say T has a shading order if there exists a sequence of exposed vertices that reduce, or whose removal reduces T to a point. Okay? It's a very algorithmic notion. It's very nice. So now there are two things where the dimensions play a role. And the first kind of nice thing that somehow one can note is so a proposition if T is planar, it always has a shedding order. So this is perhaps kind of analogous to these very nice but basic theorems that say, okay, so if I have a triangulation of a convex planar set, then it always has a shelling, for instance, or collapse. This is something that you might recall from one of these basic topologies or basic simplicial topology sessions. And basically, it's something that probably Bruno might mention. This is something very basic. And then there's a theorem that is also very familiar to something that I did with Bruno during my PhD and his postdoc time, and this is the following. If T is a fin of any dimension, then after sufficiently many barycentric subdivisions, it gets a shedding order. Then after sufficiently many barycentric subdivisions, it has a shedding. Okay. So it's actually somehow things that somehow Bruno and I could have done, yeah, a little bit more than 10 years ago. But, you know, sometimes you don't. Bruno and I certainly knew about this conjecture back then because Frank told us about it. But somehow, sometimes you don't try because, you know, conjecture seems too intimidating. But it's somehow we could have done it. It's something we missed. So this is the theorem, and from there the order conjecture is kind of simple. Let me not try to kind of go into the proof of this. It's not so hard, but it's a little bit technical. But the basic intuition is still planar. It's just reconstructing this kind of basic nice decomposition order from the planar case in higher dimensions. And so I will try to explain why I can always find it in the plane, and the situation is really simple, but also really nice. So I will go back to some fin, and I will try to explain why it's easy to find in the plane, the shedding order, and from there kind of then I'm out of time. So I will just draw some random scaled fin. I will just do it like this. This. Okay. I will just so I have my scaled fin, right? The only thing I have to prove is that there exists an exposed vertex. All right. So how do I do that? So I just orient the plane in some way. Oh, let me do it like this. I read off the horizon in some way. The horizon is now a one-dimensional disk. So you see already there's some kind of induction going on. Now I only have to analyze a one-dimensional disk in a sense, I think. And now what do I do? I look at the vertices of the horizon in this order, right? So I have this vertex here, 1, 2, 3, 4, 5. Okay. And the next step is I look at the edges or the edges that are incident to my boundary vertex, to my boundary vertices, right? So incident to these boundary vertices that are not parallel, right? So the closest edge that is not in the horizon and not does not contain B in its affine hull. So the closest edge here would be this one here, right? This would be the closest edge, and it kind of points downwards towards the horizon, right? So this one, so I write down the first vertex and I start with the down, because this edge here pulls down. Then I'm looking at the second vertex and I'm going in this orientation, and it points up. And then at the third vertex, okay, so the next one here, it points down again. And then I have one that pulls up. So I claim that I have found an exposed vertex, W exposed, if there's 3 cases. So I start with the sequence of downs and ups. It starts with a down. 2, it ends with an up. Or 3, there's a subword that is basically just up and down. So there's one down that follows immediately on an up. Okay? So I claim that, okay, so clearly this is true, right? So down, if I have the down here, this vertex is exposed. If I have an up here, this vertex is exposed. Up, down, here at this vertex, up, down. And so, I mean, of course I can try to avoid this. I can ask, okay, I mean, is there no configuration that avoids this? Well, but notice that if T avoids 1, it has to start with an up. It starts with an up. If T also avoids 2, it ends with the down, with D. All right, so you start with up and you end with down, but then somewhere in the middle you have to have up following down, down following up, and this is, so you cannot avoid up down, somewhere in the middle. So the third one you have to at some point satisfy. So you see, if I avoid first and the last, the third one kicks you, and that's it. In the plane, this once you realize that you reduce to the situation, it's really simple. And now the next step is you have to show that kind of the analog of this, some analog of this is true in higher dimensions, and then this theorem comes in. All right, so this theorem okay, so it's not true immediately. You can easily show that. But what you can show is that after some sufficient barycentric subdivision, you can find a shedding order, and that's it. So from there, the rest of the theorem is kind of simple. And but I'm also out of time, so I thank you for your attention. And